The next topic I want to talk about is something called a partition. And right now it'll be kind of unclear why this is an important concept, but once we get further into the course, we're going to use this quite a bit. It's in fact related to a very important concept called equivalence relations. So let me tell you what a partition is. A partition, you can think of it, if this is a set, a partition is basically breaking up that set into a bunch of non-overlapping chunks. And you have to be careful about it. It can't just be anything. So there are 3 conditions that we have to satisfy for something to be a partition. So it's a set of subsets that satisfy the following 3 conditions. So for each subset in our set, can't be empty. We don't want an empty set in there because that's kind of superfluous. The next condition is that, well, any 2 of these subsets here and an M, they have nothing in common. There's no overlap. We're actually breaking up the set into separate chunks. So the intersection of any 2 sets in there that are distinct is the empty set. And the third condition is that if you take the union of these over all sets in our partition, you get everything. So that's basically saying that every element of your set A is in one of these chunks. So again, quickly, it says that there's no superfluous sets and there's no empty sets. Every set of 2 sets, if you take the intersection, it's empty. None of these subsets have anything in common, so it's chunking up the entire set. And this says that you have everything. If you take the union of all your chunks, you end up with the original set. So let's look at an example. Let's see how this works. So let's call Z sub E the set of even integers, and Z sub O the set of odd integers. And let's ask, is this set here, which is, we'll call it S, and it just contains the sets ZE and ZO, a partition of the integers. So first of all, let's check if this is even possible. So is S a set of subsets of Z? And here, well, we know that the even integers, every even integer is indeed an integer. So that's good. And every odd integer is an integer. So that's good. So it looks like it's even possible. So this set makes sense to talk about. That's good. It's a possible partition. Everything in there makes sense. So now we just need to check the 3 conditions. Condition 1. Is the empty set an element of S? And clearly, in this case, it's not, so we're good to go. That condition is satisfied. There's only 2 elements of our set here. Remember, the elements of the set are subsets. It is the even integers and the odd integers. Okay? Second one, there's only 2 elements, so we can just check it. What is the intersection between even integers and odd integers? Keeping in mind that 0 is even. 2 times 0 is 0. So 0 is an even integer. So what integers are both even and odd? And the answer is, of course, none of them. So the intersection of those 2 sets is indeed empty. Okay, and we have them all. So let's check condition 3 here. what is the union of ZE with ZO? And the reason I wrote it like this is because it's a union of just two sets, so we can just use kind of the regular union notation here. And that is, of course, well, all integers are either even or odd. We're not missing anything out. We get everything back. So this is indeed a partition. So yes, S is a partition of the integers. Every integer is either even or odd, and we covered them all. Okay, let's look at a little example here. And maybe I'll let you guys try this. So we'll have our set here be the numbers from 1 to 10. The counting numbers from 1 to 10. I'll do the first one just to make sure that we understand everything. So is S1 here? Is this a partition of A? And the answer, you have to be a little careful. The answer is no. The elements of S1 are indeed elements of A, not subsets of A. Remember, partitions have elements being subsets. So this is indeed not. So the answer is no, because elements are not subsets of A. So that one was pretty easy. So I think you guys should try the rest, 2 through 9. Pause the video now. Think about each one. Remember, make sure that they're satisfying the definition for a partition. They need to have the elements of your partition need to be subsets of your original set, and they need to satisfy those 3 different properties. There's no superfluous empty sets in there. Every subset is mutually exclusive. They don't share any common elements. And if you union all the subsets together, you get the original set back. You're not missing any elements in those subsets. So think about that and give it a go. Okay, now that we're back, well, what about S2? Well, S2 has 1 element in it. It's a subset, so it passes that. Is there an empty set in S2? There is not an empty set, so the first condition is passed. The second condition, let me scroll up again so we can read it carefully. It says, for any 2 distinct sets, N and M. Here, there is only 1 set in S2. S2 has 1 element, and it's the set from 1 to 10. So S2, in fact, is vacuously true because this sentence does not apply to it. It basically says if N and M are distinct sets that are elements of S, so distinct subsets, then their intersection is the empty set. But the if part is never true. You can't pick 2 distinct sets from here because there's only 1. So 2 is vacuously true. Okay, we know 2 is vacuously true. And the union of all sets, we get our original set back. And here we're just taking an indexed union of 1 set, so there's nothing really to do. It's just this set. So that is the entirety of A. So we are good to go. So it passes condition 3. So all 3 conditions of being a partition are satisfied. So this is, yes, it is a partition. The next one, same idea. Let's have a look. So the elements here are subsets. of our set A, we're good to go. Is condition 1 satisfied? Is the empty set an element here? It is not. That's fine. Condition 1 is passed. These are one element sets. This one has 1 in it. This one has 2 in it. You have 3, 4, 5, 6, 7, 8, 9, and 10. Obviously, if you take the intersection of any of these, you get the empty set because they have no elements in common. That's great. And if you take the union of all of these sets, you get back 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this passes all 3 conditions. This is indeed a partition. The next one, S4. Well, it is a set of subsets, but the empty set is an element of S4. That's no good. That fails condition 1. So 1 failed. Now just circle the 1 to say it's condition 1. S5. Well, here we have 2 sets. So the elements are subsets of A. That's great. The empty set isn't in here, so passes condition 1. These are all of the odd numbers. These are all of the even numbers. So the intersection of these 2 sets is the empty set. That's great. Condition 2 is satisfied. They don't share any elements. Condition 3, if we take the union of all of these sets, do we get back with our original set? We do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got them all. This is indeed a partition. What about this one? So we have the subset of even numbers in A, the subset of square numbers in A, and 3, 5, 7. So let's write this down. So this one we have to be a little more careful. The even numbers, we can just write them out. 2, 4, 6, 8, 10. Square numbers in A, 1, 4, 9, and 3, 5, 7. So all of these 3 elements are indeed subsets of A. That looks good. Condition 1 is satisfied. None of these are the empty set. That's good. However, look at this. If I take the intersection of, let me call this set, let's call it T, and I'll call this set U. The intersection of T and U has something in common. It has the element 4. It's in both sets. It's both a square number and an even number. So that's not good. That means this is not a partition. We didn't break up the set, so it's in separate chunks. 4 is shared between these 2 chunks, so it's not a partition. So no, because 2 is failed. Okay. Let's look at S7 now. So here we have a indexed union of sets. So it goes from I equals 3 to 5. And it says that each set has, it's the numbers in A that have I letters in their English words when you write it out. So let's look at what this is. So the first set is going to be when I equals 3. So it's going to be all the English words of the numbers that have 3 letters in them, okay? So we have 1, we have 2, we don't have 3, we don't have 4, we don't have 5, we have 6, we don't have 7, we don't have 8, we don't have 9, but we have 10. Union, well, the ones with 4 letters, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we'll union 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is when I equals 3. It's elements of A that have 3 letters in its English word. This is 4 letters in its English word. This is 5 letters in its English word, from 3 to 5. Now we have to be careful. It kind of looks like a partition. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It looks like we have them all. No empty sets and no elements are shared between any of these sets. But remember, this is an indexed union. This isn't 3 separate sets. This entire set ends up being 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So, in fact, what we have here is the exact same as S2. There is one element of S7, and that element is the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the same as S2. So I'm going to mark that down. This is yes, same as S2. And I want to talk about this for a second. If instead, if S7 looked like this, if it was just these sets, not the union of them, but the separate sets, 1, 2, 6, 10, and then 4, 5, 9, and then 3, 7, 8. Now this would be a partition, a different partition, but this would be a partition. Here we have a partition, but it's the same partition as S2. Even though it looks like 3 different sets, remember, it's the union of these 3 sets, which ends up being all of the numbers. So it's subtle, but it's different. S8, you can see the only difference here is that we're starting at 2. And there's no numbers here that have 2 letters in their word. So the difference between S7 and S8 would be at the start you have, I'll do this in blue, you would have a union of the empty set. So this is when I equals 2. There's nothing in that set. There's none of these numbers have 2 letters in their English word. So the empty set when I equals 2, I equals 3, I equals 4, I equals 5. But again, you're taking a union of these guys, which is just this set here. If S8 instead of a union was those separate things, it would be untrue, because now you would have the empty set as one of your sets, and then 1, 2, 6, 10, and then 4, 5, 9, and then 3, 7, 8. So if it looked like that instead, or instead of being the union of these sets, it was just these sets as elements, this wouldn't be a partition. This isn't the same as S2 anymore. And then finally, let's look at S9. S9, we have to be a little bit careful. If we notice, we have this element 0 there. And 0, of course, isn't in A. It's not an element of A. So if I call this set, let's call this M, and this set N, then here the answer is no, since N isn't a subset of A, because there's an element, 0, that's not in A. So just kind of the definition of the set doesn't make sense. And that is the idea of a partition. Remember, there's 3 things. Again, let me draw this diagram. And that's kind of the easiest way to think about it. There's 3 things that you have to care about. First of all, let me put some elements in too. There are my elements in this set. So the first thing that you care about is that each set has something in it. There are no empty sets. There are no superfluous sets. The second thing is that none of these sets share any elements. That's all partitioned off, so maybe something like that. And if you take the union of the sets that are broken up, you recover the original set. And that's how partitions work.